Imagine a question so profound, so fundamental, that it challenges the very limits of human understanding. What existed before the Big Bang? It's a question that has haunted physicists and philosophers for generations, a cosmic riddle wrapped in an enigma, served with a side of mind-bending paradoxes. Was there truly a before? Our understanding of time itself is intrinsically linked to the existence of the universe. Time, as we perceive it, began with the Big Bang. So, asking what happened before might be akin to asking what's north of the North Pole. It might simply be a question that doesn't have a scientifically meaningful answer within our current framework, but that hasn't stopped scientists from trying to peek behind the curtain of creation. The very idea of nothingness is far more complex than it seems. It's not simply empty space devoid of everything. In the realm of quantum physics, nothing is actually a seething cauldron of virtual particles, constantly popping into and out of existence, fleetingly borrowing energy from where? Or perhaps, from when? These aren't just abstract concepts. These are the very foundations on which our reality is built. Imagine, if you will, a vast, boundless ocean of pure energy, an energy field permeating everything, even what we perceive as empty space. This field, some physicists propose, might have existed in a state of incredible density and uniformity before the Big Bang, a state so unlike anything we can comprehend that our everyday laws of physics simply break down. Think about the concept of a singularity, a point of infinite density and temperature. This is often described as the starting point of the Big Bang, a theoretical point where all the mass and energy of the universe was compressed into an infinitely small space. But what triggered this singularity? What caused it to explode outwards in the event we call the Big Bang? Some theories propose that the singularity was not the beginning, but rather a transition point. Perhaps our universe is just one of many, existing within a larger multiverse. Each universe potentially with its own set of physical laws and constants. Our Big Bang, in this scenario, could have been triggered by the collision of two such universes, a cosmic fender bender on an unimaginable scale. Others explore the idea of a cyclical universe, where the universe expands and contracts in an endless cycle of big bangs and big crunches. Our current expansion might simply be one phase in this never-ending cosmic dance. The before the Big Bang, in this case, would be the previous contraction phase, a period of unimaginable heat and density, ultimately leading to another explosive rebirth. Perhaps the question itself is flawed. Maybe the concept of a linear timeline is a construct of our limited human perception. Maybe before and after are meaningless in the context of the universe's ultimate origin. Could it be that the Big Bang wasn't a beginning, but a transition from a state we simply lack the tools to comprehend? And so the question of what came before continues to echo through the corridors of theoretical physics. But perhaps, instead of looking backward into an unknowable past, we should focus on the moment of creation itself, the very instant the universe burst into existence. Imagine, if you will, all the mass and energy of existence compressed into a space smaller than an atom. It's a concept so extreme, it's almost impossible to visualize. This is the singularity, a point of infinite density, the theoretical launch pad for everything that exists. But what exactly is a singularity? It is not simply a tiny dot. It is a point where our current laws of physics break down entirely. General relativity, Einstein's theory of gravity, predicts that under immense pressure, matter will collapse into a singularity. However, at this scale, quantum mechanics, the physics of the very small, should also be at play. The problem is general relativity and quantum mechanics don't play well together. When applied to the singularity, they produce nonsensical results, infinities that make no physical sense. It's like trying to fit a square peg into a round hole. The universe simply rebels. Think of it as a cosmic traffic jam, where all the known rules of the road suddenly vanish. Cars, representing the fundamental forces of nature, crash into each other in a chaotic, uncontrolled frenzy. The GPS, our understanding of physics, malfunctions, leaving us utterly lost in the primordial darkness. So, how do we resolve this crisis? Modern physics is attempting to bridge this gap through theories of quantum gravity. These theories, like string theory and loop quantum gravity, attempt to describe gravity at the quantum level, potentially smoothing out the singularity into something less singular. String theory, for example, proposes that fundamental particles aren't point-like, but rather tiny, vibrating strings. Imagine the universe is not made of individual grains of sand, but instead an intricate tapestry woven from countless shimmering threads. These strings exist in 11 dimensions, most of which are curled up and hidden from our everyday perception. At the singularity, these strings could interact in ways that prevent the formation of a true point of infinite density. Loop quantum gravity, on the other hand, suggests that space-time itself is quantized, meaning it comes in discrete units like pixels on a screen. Imagine space is not a smooth, continuous fabric, but rather a mosaic of tiny, indivisible tiles. At the singularity, the size of these tiles would become incredibly small, preventing space-time from collapsing into an infinitely small point. Now consider the sheer intensity of energy crammed into this infinitesimally small space. We're talking about energy levels that dwarf anything we can create in even the most powerful particle accelerators. The conditions within the singularity would be so extreme that fundamental forces like gravity, electromagnetism, and the strong and weak nuclear forces might have been unified into a single superforce. It's like a cosmic pressure cooker, where the laws of nature are bent and twisted beyond recognition. This unified force, if it existed, remains a tantalizing mystery, a holy grail for physicists seeking to understand the universe's ultimate origins. The singularity, therefore, is not just a point of breakdown, but also a point of immense potential. It's the theoretical launchpad for everything that exists, the source from which all matter, energy, and space-time itself emerged. It represents the ultimate test of our understanding of physics, a frontier where the known meets the unknown, where the possible blurs with the seemingly impossible. The secrets held within this cosmic seed may unlock the deepest mysteries of our universe, from its birth to its ultimate fate. But even as we grapple with the incomprehensible nature of the singularity, a new enigma emerges, a cosmic plot twist that defies all expectations. What if the universe in its infancy experienced a growth spurt so explosive, so unimaginably rapid, that it dwarfs even the most extreme events we can conceive? This is the mind-bending theory of inflation, a fleeting moment of exponential expansion that reshaped the very fabric of reality. Imagine, if you will, a balloon being inflated not at a steady pace, but with an instantaneous burst of air. This is akin to what cosmologists believe happened in the first tiny fraction of a second after the Big Bang. In a period lasting perhaps only 10 to the power of negative 36 seconds, a time so short it makes a nanosecond seem like an eternity, the universe expanded by a factor of at least 10 to the power of 26. That's like taking something the size of an atom and instantaneously stretching it to the size of our solar system. Why such a frantic expansion? What force could possibly be responsible for this cosmic jack-in-the-box? The answer, according to many physicists, lies in a hypothetical field known as the inflaton field. Think of it as a kind of cosmic energy field that permeated the early universe. This field, unlike anything we observe today, possessed an enormous amount of potential energy. And like a ball teetering on the edge of a cliff, it was poised to release that energy in a dramatic fashion. As the inflaton field decayed, it released its pent-up energy, driving this period of accelerated expansion. But the effects of inflation were far more profound than simply making the universe bigger. It also smoothed out any wrinkles or imperfections that might have existed in the early universe. Imagine crumpling a piece of paper and then instantly stretching it to the size of a football field. The wrinkles would be ironed out, leaving a smooth, uniform surface. Inflation did much the same thing to the universe, smoothing out any initial curvature and creating the remarkably uniform cosmos we observe today. But here's where it gets even more interesting. While inflation smoothed out the universe on a grand scale, it also seeded the very structures we see today: the galaxies, the clusters of galaxies, the vast cosmic web that spans billions of light years. How could something that smoothed things out also create structure? The answer lies in the quantum realm, in the tiny fluctuations that are constantly popping in and out of existence, even in the emptiest of space. These quantum fluctuations, amplified by the rapid expansion of inflation, were stretched into macroscopic size, becoming the seeds for future structures. Think of it as blowing up a tiny grain of sand until it becomes a mountain. These mountains, these regions of slightly higher density, then acted as gravitational attractors, pulling in more and more matter over billions of years, eventually coalescing into the galaxies and structures we observe today. It's a truly remarkable concept that the very fabric of our reality was sculpted by quantum fluctuations during a period of hyper-accelerated expansion. But is there any evidence to support this mind-boggling theory? While we can't directly observe inflation, its effects should be imprinted on the cosmic microwave background, the afterglow of the Big Bang. And indeed, observations of the cosmic microwave background by satellites like COBE, WMAP, and Planck have revealed subtle temperature fluctuations that are consistent with the predictions of inflation. These fluctuations, these tiny variations in temperature, are like fingerprints on the infant universe, providing tantalizing clues about its earliest moments. It is as if we are decoding an echo from the universe's birth. Inflation also helps solve some of the major cosmological puzzles that plagued the standard Big Bang model. For example, the horizon problem. How can the universe be so uniform in temperature when regions on opposite sides of the sky are so far apart that they could never have been in causal contact? Inflation solves this problem by proposing that these regions were once much closer together, in causal contact, before being rapidly separated by the exponential expansion. Think of it as stirring a cup of coffee and then instantly expanding the cup to the size of the Earth. The coffee would still be uniformly mixed even though the edges of the cup are now incredibly far apart. Another puzzle is the flatness problem. Why is the universe so close to being geometrically flat? General relativity predicts that the universe should be either curved like a sphere or curved like a saddle. But observations suggest that it is remarkably flat, like a tabletop. Inflation solves this problem by stretching out any initial curvature, making the universe appear much flatter than it actually is. It's like inflating a balloon to such an enormous size that its surface appears flat, even though it's still technically curved. Despite its successes, inflation is not without its challenges. One of the biggest questions is what exactly caused inflation to start and stop? What was the nature of the inflaton field? And what triggered its decay? These are questions that continue to baffle physicists and drive ongoing research. Some theories propose that inflation is eternal, meaning that it never stops, creating an infinite number of bubble universes, each with its own set of physical laws and constants. Our universe in this scenario would be just one bubble in a vast multiverse. Is inflation a confirmed theory? Not yet. But it remains the best explanation we have for the early universe and its subsequent evolution. It's a bold, audacious idea that challenges our understanding of space, time, and the very nature of reality. And like all great scientific theories, it continues to be tested and refined as we probe deeper into the mysteries of the cosmos. It's a story far from complete, and the next chapter promises even more startling revelations. With the universe now vastly expanded and smoothed out by inflation, a new chapter in its story begins. But expansion alone doesn't build a universe. Where did everything come from? How did the raw energy of the early cosmos transform into the tangible stuff of stars, planets, and ultimately us? The answer, perhaps surprisingly, lies in the most famous equation in all of physics: E equals mc squared. Einstein's masterpiece reveals a profound connection between energy and matter, stating that they are, in essence, two sides of the same coin. Energy can be converted into matter, and matter can be converted into energy. But how did this cosmic alchemy play out in the nascent universe? Imagine a cauldron, not of boiling water, but of pure, raw energy. The universe, in its earliest moments, was a seething, superheated soup, hotter than the core of any star. The temperature reached trillions upon trillions of degrees, an environment so extreme that matter as we know it could not even exist. In this ultra-hot environment, photons, particles of light, possessed tremendous energy. These high-energy photons collided with each other, and in these collisions something extraordinary happened. The energy of the photons could spontaneously transform into pairs of particles, matter and antimatter. For every particle of matter created, an identical twin of antimatter was also born. These weren't the familiar protons and neutrons that make up our world today. Instead, the first particles were the fundamental building blocks of matter: quarks and leptons, the smallest known constituents of reality. Quarks, with their whimsical names like up, down, strange, charm, top, and bottom, would eventually combine to form protons and neutrons. Leptons, including the familiar electron, would orbit the nucleus of atoms, carrying electric charge. Picture a particle zoo, a chaotic menagerie of exotic creatures popping into and out of existence. Quarks and antiquarks, electrons and positrons, muons and antimuons, neutrinos and antineutrinos. The universe in its first microseconds was a truly bizarre place, a quantum carnival of ephemeral particles. Each particle had its antimatter counterpart, an identical twin with an opposite charge. When matter meets antimatter, they annihilate each other in a burst of pure energy, returning to the photons from whence they came. Think of it like a cosmic dance, a frenetic waltz of creation and destruction. Particles and antiparticles constantly appearing and disappearing, driven by the intense energy of the early universe. But as the universe expanded and cooled, this dance began to change. The energy density decreased, making it harder to create new, massive particles. The particle zoo began to thin out, and the universe started its transition from a sea of energy to a sea of matter. This period of particle creation and annihilation lasted for only a tiny fraction of a second, perhaps a few microseconds. But in that fleeting moment, the fate of the universe was sealed. The transition from pure energy to the building blocks of matter was a pivotal step in cosmic evolution, setting the stage for the formation of atoms, stars, galaxies, and ultimately, life itself. But there's a deeper mystery lurking beneath the surface, a question that continues to challenge our understanding of the universe. But this seemingly balanced equation of creation and destruction hides a profound asymmetry, a cosmic imbalance that tilts the scales of existence in favor of matter. It's a question that cuts to the heart of reality. Why is there something rather than nothing? In the fiery crucible of the early universe, matter and antimatter were created in equal amounts, or so we thought. But if that were the case, a catastrophic annihilation should have occurred as the universe cooled. Every particle of matter would have met its antimatter counterpart, and they would have utterly destroyed each other in a spectacular burst of energy. The universe would be filled with light, but utterly devoid of the stuff that makes up stars, planets, and us. Instead, we live in a universe dominated by matter. Galaxies swirl with stars made of protons, neutrons, and electrons, not their antimatter twins. So how did matter win out? How did this slight, almost imperceptible advantage arise in the first moments of creation? It's a puzzle that has vexed physicists for decades, a cosmic whodunit with few solid clues. One leading theory involves a process called baryogenesis. Baryons, like protons and neutrons, are the building blocks of ordinary matter. Baryogenesis proposes that some unknown interaction in the early universe violated the perfect symmetry between matter and antimatter, creating a tiny excess of matter particles. Imagine a cosmic coin toss, where matter and antimatter are equally likely to appear. But what if the coin was slightly weighted, just a fraction of a percent, in favor of matter? Over countless coin tosses, this tiny bias would add up, leading to a significant surplus of matter over antimatter. But what could have caused this bias? Physicists have proposed several mechanisms, many of which involve exotic particles and forces beyond the standard model of particle physics, the current best theory describing the fundamental building blocks of the universe. Some theories suggest that heavy particles decaying in the early universe might have favored the production of matter over antimatter. Other ideas involve new fundamental forces that interact differently with matter and antimatter. One intriguing possibility is that neutrinos, those ghostly, elusive particles that barely interact with matter, could hold the key to this asymmetry. Certain types of neutrinos might violate what is known as charge parity symmetry, meaning that they behave differently from their antimatter counterparts. This subtle difference could have tilted the scales in favor of matter during the early universe. It is an interesting fact that neutrinos are so light, and the difference in mass between types of neutrinos could cause an imbalance when the matter-antimatter annihilation happened in the early universe. Experimentally, scientists are recreating conditions like those after the Big Bang in sophisticated and expensive experiments to try and recreate the matter-antimatter imbalance. To date, these experiments have shown that the current standard model that physicists have accepted cannot cause enough matter over antimatter to account for the asymmetry. The search for the origin of this matter-antimatter asymmetry is a cornerstone of modern cosmology. The answer to this riddle might not only explain why we exist, but also reveal new physics beyond our current understanding. It could be that the universe itself favors one flavor over another, and that the universe is not indifferent to matter or antimatter. Without this slight imbalance, the universe as we know it would not exist. There would be no galaxies, no stars, no planets, and certainly no people to ponder these cosmic mysteries. The universe would be a vast, empty void filled with nothing but energy. The very existence of our matter, dominated cosmos, hinges on this delicate asymmetry, a profound mystery which leads us to the assembly of those building blocks. So, a slight asymmetry in the very fabric of existence allowed matter to prevail over antimatter. But this excess matter was not yet the familiar stuff of our everyday world. The universe was still too hot, too energetic for stable atoms to form. It was a period of transition, a cosmic adolescence where the fundamental building blocks were just beginning to assemble. But how exactly did this happen? How did the primordial soup of quarks and leptons coalesce into the protons and neutrons that would eventually form the nuclei of all the atoms in the universe? Imagine a cosmic construction site where tiny particles are buzzing around like hyperactive workers, frantically trying to find their place in the grand design. The temperature is still incredibly high, several trillion degrees, but it's cooling rapidly as the universe continues to expand. This cooling is crucial, as it allows the fundamental forces of nature to begin to exert their influence. One force in particular, the strong nuclear force, plays a starring role in this stage of cosmic evolution. Think of the strong force as the universe's most powerful glue, an irresistible attraction that binds quarks together to form composite particles. But the strong force isn't just any ordinary glue. It's a force that gets stronger as you try to pull quarks apart. It's as if the quarks are connected by incredibly strong springs, resisting any attempt to separate them. Now, picture 3 quarks, each with a different color charge, red, green, and blue, swarming through the cooling plasma. The strong force acts upon these quarks, drawing them together. These quarks can combine in a specific way, forming a stable, neutral particle. This particle is no other than a proton, the positively charged particle that resides in the nucleus of every atom. Another combination of quarks can occur when three quarks form another neutral particle, this time a neutron. Neutrons, as the name suggests, have a neutral charge and exist in the nucleus with the protons. But why these specific combinations? Why not two quarks or four? The answer lies in the mathematics of the strong force, which dictates that only combinations of quarks with a neutral color charge are stable. Think of it like assembling a puzzle, where only certain pieces fit together to create a complete picture. Three quarks, one red, one green, and one blue, form a color-neutral combination, a stable and enduring structure. These protons and neutrons, forged in the crucible of the early universe, are the foundation upon which all matter would be built. They are the heavyweights of the atomic nucleus, providing the mass and stability that would allow atoms to form and endure. But their creation was not a simple, straightforward process. It required precise conditions, a delicate balance of temperature, density, and energy. Think of it like baking a cake. If the oven is too hot, the cake will burn. If it's too cold, the cake will never rise. Similarly, the formation of protons and neutrons required the universe to cool to just the right temperature, allowing the strong force to work its magic without disrupting the fragile balance of the primordial soup. This transition, from a universe dominated by fundamental particles to one populated by protons and neutrons, marked a significant milestone in cosmic evolution. These newly formed particles were the seeds of all future atoms, the building blocks of stars, planets, and life itself. And with their creation, the universe was poised for its next great act of alchemy, the forging of the first elements. But as the protons and neutrons began to coalesce, a tantalizing question arises. What elements came first, and what processes led to their creation? And with their creation, the universe was poised for its next great act of alchemy, the forging of the first elements. But as the protons and neutrons began to coalesce, a tantalizing question arises. What elements came first, and what processes led to their creation? Imagine the universe as a gigantic, superheated reactor, a cosmic kitchen where the most basic ingredients of matter are being cooked up in a frenzy. The clock is ticking, the universe is expanding and cooling, and the window of opportunity for element formation is rapidly closing. This epic event, known as Big Bang nucleosynthesis, or BBN, unfolded in the first few minutes after the Big Bang, a period of primordial alchemy that shaped the elemental composition of the cosmos for billions of years to come. Now, what were the key ingredients in this cosmic recipe? The primary players were protons and neutrons, the building blocks of atomic nuclei. But there was also a crucial supporting cast of electrons, neutrinos, and photons, all interacting in a complex dance governed by the fundamental forces of nature. As the universe cooled to around 1 billion degrees Celsius, a temperature still incredibly hot but cool enough for nuclear reactions to occur, protons and neutrons began to collide with tremendous force. These collisions weren't random. They followed specific rules dictated by the laws of nuclear physics. Protons and neutrons could fuse together, forming heavier nuclei, but only under certain conditions. The simplest nuclear reaction involved the fusion of a proton and a neutron, creating a nucleus of deuterium, a heavy form of hydrogen. Deuterium, with one proton and one neutron, is like the first rung on the ladder of element formation. From there, deuterium could fuse with another proton or neutron, creating helium-3, an isotope of helium with 2 protons and 1 neutron. But the real prize was helium-4, the most stable and abundant isotope of helium with 2 protons and 2 neutrons. Helium-4 formed through a variety of pathways, including the fusion of 2 deuterium nuclei or the fusion of helium-3 with a neutron. The universe was rapidly becoming enriched with these light elements, hydrogen, deuterium, and helium. But why did the primordial alchemy stop there? Why didn't the early universe forge heavier elements like carbon, oxygen, or iron, the elements essential for life as we know it? The answer lies in the conditions prevailing during Big Bang nucleosynthesis. The universe was expanding and cooling so rapidly that there simply wasn't enough time for heavier elements to form. Creating heavier elements requires overcoming significant energy barriers. To fuse heavier nuclei, you need even higher temperatures and densities, conditions that only exist in the cores of stars. Think of it like trying to build a house in a hurricane. The strong winds and torrential rain make it almost impossible to assemble the structure. Similarly, the rapid expansion and cooling of the early universe hindered the formation of heavier elements. Furthermore, certain elements, like beryllium-8, are inherently unstable, decaying almost instantaneously. This instability created a bottleneck in the element formation process, preventing the universe from forging heavier elements beyond helium in significant quantities. So, the Big Bang nucleosynthesis was a brief but crucial period in cosmic history, a fleeting moment where the elemental composition of the universe was largely determined. The universe emerged from this era with a composition that was roughly 75% hydrogen and 25% helium, with trace amounts of deuterium and lithium. But is there any evidence to support this theory of Big Bang nucleosynthesis? Can we actually test these predictions about the elemental composition of the early universe? The answer, remarkably, is yes. By studying the oldest, most pristine objects in the universe, astronomers can measure the primordial abundances of light elements. These objects, like distant gas clouds and ancient stars, provide a glimpse into the universe's past, allowing us to test the predictions of Big Bang nucleosynthesis with incredible precision. And the results are striking. The observed abundances of hydrogen, helium, and lithium in these ancient objects match the predictions of Big Bang nucleosynthesis with remarkable accuracy. This agreement is one of the strongest pieces of evidence supporting the Big Bang theory, a testament to the power of scientific modeling and observation. Imagine that, the elemental makeup of everything that surrounds us, from the air we breathe to the ground we walk on, was largely determined in the first few minutes after the Big Bang. It's a humbling thought, a reminder of our deep connection to the cosmos. You might be wondering, then how did heavier elements come to be? If the Big Bang couldn't forge carbon, oxygen, iron, and all of the other heavy elements we observe today, where did they originate? The answer, as it turns out, lies in the heart of stars, those cosmic furnaces that burn brightly for billions of years. Stars, through a process known as stellar nucleosynthesis, are the ultimate alchemists, forging heavier elements from lighter ones. It is a stellar journey we will travel together, but not before delving into another equally important element of understanding the cosmos, by visualizing the early universe as a hot, dense plasma. But even as the universe settled into its elemental composition, an extraordinary transformation was about to occur, a cosmic stage setting that would dramatically alter the way light itself moved through the cosmos. Imagine, if you will, the universe as a vast, swirling fog, a dense and impenetrable cloud where light struggles to find its way. For the first 380,000 years after the Big Bang, the universe was opaque, a cosmic fog perpetually obscuring the view. Why this cosmic opacity? The answer lies in the state of matter at that time. The universe was not filled with neutral atoms as it is today. Instead, it was a hot, dense plasma, a seething soup of protons, helium nuclei, and free electrons. These electrons, unattached to any atom, were the key players in creating this cosmic fog. Think of it as a crowded dance floor, where photons, the particles of light, are constantly bumping into the dancers, the free electrons. Light simply couldn't travel freely through this dense plasma. Every time a photon tried to move, it would immediately collide with an electron scattering in a random direction. This process, known as Thomson scattering, made the universe utterly opaque, like trying to see through a dense cloud of smoke. Imagine trying to navigate through a crowded room blindfolded. You would constantly bump into people, unable to move in a straight line or see where you are going. This is what it was like for photons in the early universe, trapped in a perpetual game of cosmic pinball. Why couldn't these electrons simply combine with the protons and helium nuclei to form neutral atoms? The answer is temperature. The universe was still incredibly hot, thousands of degrees Celsius. At these temperatures, electrons have so much energy that they cannot bind to atomic nuclei. Any attempt to form a neutral atom would be immediately thwarted by the high-energy photons, which would instantly knock the electron loose. It was like trying to build a sandcastle at high tide, the waves constantly washing away your efforts. This era, known as the cosmic fog, was a crucial period in the universe's history, a time when light was trapped and unable to travel freely. It was a period of darkness, a time before stars, before galaxies, before any of the structures we see today. It was a time when the universe was simply too hot to see through. The journey of light in the early universe would soon take a dramatic turn, paving the way for the cosmos we know today. But as the protons and neutrons began to coalesce, a tantalizing question arises. What elements came first, and what processes led to their creation? But there was one more hurdle to clear, one final transformation that would forever change the universe's relationship with light. Imagine, if you can, being trapped inside a dense fog bank, unable to see more than a few feet in front of you. That was the reality for photons in the early universe, constantly scattered and absorbed by the hot, dense plasma. But the universe was about to clear, the fog was about to lift, and the light of creation was about to be unleashed. So how did this cosmic fog dissipate? What was the pivotal moment that allowed light to finally travel freely through the universe? The answer lies in a process known as recombination, a deceptively simple name for a profoundly important event. Recombination occurred around 380,000 years after the Big Bang, a cosmic blink of an eye compared to the 13.8 billion year age of the universe. By this time, the universe had expanded and cooled to a mere 3,000 degrees Celsius, a temperature that, while still scorching by human standards, was cool enough to allow electrons to combine with protons and helium nuclei, forming neutral atoms. Think of it as a cosmic matchmaking event where free electrons are finally able to find their atomic partners. The universe was still expanding, cooling down, which reduced the number of high-energy photons in the universe. There was not enough energy to disrupt stable atoms. And with this union, the universe underwent a dramatic transformation. The once ubiquitous free electrons, the primary obstacles to light's journey, were now locked up within neutral atoms. The fog began to dissipate, the universe became transparent, and photons were finally free to travel unimpeded across the vast expanse of space. But this wasn't just any light. These photons, released during recombination, have been traveling through the universe for billions of years, carrying with them a snapshot of the early cosmos. Today, we observe these photons as the cosmic microwave background, or CMB, the afterglow of the Big Bang. Think of the CMB as a baby picture of the universe, a faint echo of creation that has been stretched and cooled by the expansion of space. It's a nearly uniform bath of microwave radiation permeating the entire sky, a testament to the universe's hot, dense past. But within this uniformity lie subtle temperature fluctuations, tiny variations that hold the key to understanding the formation of galaxies and large-scale structures. These temperature fluctuations, only a few millionths of a degree Celsius in magnitude, are like fingerprints on the infant universe, providing invaluable clues about its earliest moments. They represent the seeds of future galaxies, the regions of slightly higher density that would eventually collapse under gravity to form the structures we observe today. The CMB is not just a theoretical prediction. It is a real, observable phenomenon that has been studied by generations of astronomers using increasingly sophisticated telescopes. Satellites like COBE, WMAP, and Planck have meticulously mapped the CMB. revealing its intricate patterns and confirming the predictions of the Big Bang Theory with stunning precision. Imagine seeing a relic of the past in perfect condition billions of years after it happened. Perhaps you are asking yourself, what does this radiation tell scientists? The CMB tells scientists the age, the makeup, and geometry of the universe. It is an important observation that helps scientists better understand the universe, but the discovery of the CMB was not without its surprises. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were working on a new microwave receiver at Bell Laboratories in New Jersey. They were puzzled by a persistent background noise, a faint hiss that seemed to be coming from all directions in the sky. They tried everything to eliminate the noise, checking their equipment, cleaning the antenna, even chasing away pigeons that were nesting inside. But the noise persisted. Little did they know that they had stumbled upon one of the most important discoveries in the history of cosmology. Meanwhile, just a few miles away at Princeton University, a team of physicists, led by Robert Dicke, were preparing to search for the very same radiation. When Penzias and Wilson learned of Dicke's work, they realized the significance of their discovery. They had detected the cosmic microwave background, the afterglow of the Big Bang. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their discovery, forever cementing their place in the annals of scientific history. The CMB has become one of the cornerstones of modern cosmology, providing unparalleled insights into the origin, evolution, and composition of the universe. But as the universe transitioned from a hot plasma to a transparent expanse filled with the faint glow of the CMB, a new era was about to begin. An era of darkness, before the first stars ignited and galaxies blazed into existence. What secrets did this cosmic dark age hold, and how did the universe eventually emerge from this period of obscurity? Imagine a cosmic detective story, where the evidence isn't hidden in dusty archives or crime scenes but etched across the entire sky in the form of microwave radiation. These aren't just any microwaves, these are the oldest light in the universe, a relic from a time when the cosmos was a mere 380,000 years old. This ancient light, the cosmic microwave background, or CMB, is like a giant cosmic canvas painted with the faint whispers of the early universe. But how do we decode this echo? How do we extract meaningful information from this seemingly uniform bath of radiation? The answer lies in tiny temperature fluctuations, subtle variations in the CMB's intensity that are almost imperceptible to the naked eye. These fluctuations, only a few millionths of a degree Celsius in magnitude, are the key to unlocking the secrets of the early universe. Think of them as seeds scattered across the cosmic canvas that would eventually grow into the galaxies and large-scale structures we see today. But mapping these incredibly faint fluctuations is no easy task. It requires sophisticated instruments, advanced technology, and a dedicated team of scientists willing to push the boundaries of human knowledge. Enter COBE, the Cosmic Background Explorer, a satellite launched by NASA in 1989 with a mission to map the CMB with unprecedented accuracy. Imagine a spacecraft orbiting the Earth, shielded from the sun's glare, meticulously scanning the sky and recording the faint whispers of the early universe. COBE's results were groundbreaking. It confirmed that the CMB had a black-body spectrum, a telltale sign that it was indeed the afterglow of the Big Bang. But more importantly, COBE detected the first evidence of temperature fluctuations in the CMB, providing tantalizing clues about the origin of cosmic structure. These early findings earned two of COBE's principal investigators, George Smoot and John Mather, the Nobel Prize in Physics in 2006. A testament to the profound impact of their work. But COBE was just the beginning. Scientists knew that to truly understand the CMB, they needed to probe it with even greater precision and sensitivity. That's where WMAP, the Wilkinson Microwave Anisotropy Probe, comes in. Launched in 2001, WMAP was designed to build upon COBE's legacy, mapping the CMB with even higher resolution and accuracy. Think of WMAP as a more powerful microscope, allowing us to see the universe's baby picture in sharper detail. WMAP spent 9 years meticulously scanning the sky, collecting data that would revolutionize our understanding of cosmology. Its observations allowed scientists to determine the age of the universe with unprecedented precision. 13.772 billion years, give or take 0.059 billion years. It also provided a more accurate measurement of the universe's composition, revealing that it is made up of only 4.6% ordinary matter, 24% dark matter, and 71.4% dark energy. These findings were a game changer, confirming the Lambda CDM model as the standard model of cosmology, a framework that describes the evolution of the universe from the Big Bang to the present day. But even WMAP had its limitations. To truly unlock the secrets of the CMB, scientists needed an even more powerful instrument, one that could probe the universe's earliest moments with unparalleled sensitivity. Enter Planck, the European Space Agency's flagship cosmology mission, launched in 2009. Planck was designed to map the CMB with the highest resolution and sensitivity ever achieved, pushing the boundaries of what was possible. Imagine a spacecraft orbiting the Earth, a technological marvel equipped with state-of-the-art detectors, capable of measuring temperature fluctuations in the CMB to an accuracy of a few millionths of a degree. Planck spent 4 years meticulously scanning the sky, collecting data that would provide the most detailed and accurate map of the CMB ever created. Its observations confirmed the predictions of the Big Bang theory with incredible precision, providing further evidence for inflation, dark matter, and dark energy. But Planck also revealed some intriguing anomalies, subtle deviations from the standard cosmological model that continue to baffle scientists today. Are these anomalies simply statistical flukes, or do they hint at something deeper, something that could revolutionize our understanding of the universe? What does the CMB tell us about the universe's geometry? Is the universe flat, curved like a sphere, or curved like a saddle? Planck's observations have confirmed that the universe is remarkably flat, like a tabletop, a finding that supports the theory of inflation. But the CMB is not just a tool for confirming existing theories. It is also a window into the unknown, a glimpse into the universe's earliest moments that can reveal new physics and challenge our current understanding. It is as though the universe is whispering secrets into our ears, and it is up to us to listen, to decode the echo, and to unlock the mysteries of the cosmos. Perhaps you are asking yourself, could there be something else that scientists might find when decoding the afterglow of the Big Bang? Could another event have happened that might have left clues in the patterns of the CMB? These questions continue to push scientists to continue to develop more sophisticated instruments that can see farther into the depths of space. But before we look any further, we must first turn our attention to the period after the CMB release and before the first stars ignited. The universe had just become transparent. The afterglow of the Big Bang, the cosmic microwave background, was streaming across space. But what happened next? What was the universe like before the first stars ignited, before the first galaxies blazed into existence? Imagine a period of cosmic adolescence, a vast dark expanse of time known as the cosmic dark ages, a time when the universe was filled with nothing but neutral hydrogen gas and darkness. Was this period truly uneventful, a cosmic lull before the storm of star formation? Or were there subtle, gradual processes at play, slowly shaping the universe we see today? Think of it as a cosmic blank canvas, a period lasting hundreds of millions of years after the CMB was released. The universe, still expanding and cooling, was a relatively homogeneous place, filled primarily with neutral hydrogen and helium. There were no stars, no galaxies, no bright lights to illuminate the darkness. It was a universe in its infancy, quietly awaiting the dawn of a new era. But this doesn't mean the Dark Ages were entirely static. Even in the absence of light, gravity was at work, slowly and inexorably pulling matter together. Imagine a vast, almost imperceptible cosmic dance, where gravity is the choreographer and hydrogen atoms are the dancers. Over vast stretches of time, gravity began to amplify the tiny density fluctuations that were imprinted on the CMB. These fluctuations, initially minuscule, grew larger and larger as gravity pulled more and more matter into the overdense regions. Think of it like sand gathering on a beach. A small ripple in the sand can gradually grow into a larger dune as the wind continues to deposit more sand in the same spot. Similarly, the tiny density fluctuations in the early universe acted as gravitational seeds, attracting more and more matter and slowly growing into larger structures. These structures weren't stars or galaxies yet. Instead, they were vast clouds of hydrogen gas, much larger and more diffuse than anything we see today. These clouds, sometimes referred to as primordial gas clouds or proto-galactic clouds, were the precursors to the first galaxies. They were the raw material from which the first stars would eventually form. But how did these gas clouds collapse to form stars? The answer lies in the interplay between gravity, pressure, and cooling. Gravity, as we've seen, was pulling the gas clouds together, but the gas also had internal pressure, a resistance to compression that was trying to push it apart. If the pressure was too high, the gas cloud would simply disperse. For gravity to win out, the gas had to cool down, reducing its pressure and allowing gravity to take over. How did these primordial gas clouds cool down? This is a question that scientists are still actively researching. One possibility is that the gas cooled through the emission of radiation. Hydrogen atoms, even in their neutral state, can emit photons, particles of light, under certain conditions. This emission of radiation carries away energy, causing the gas to cool down. Another possibility is that the gas cooled through collisions between hydrogen atoms. When hydrogen atoms collide, they can transfer energy, leading to a net cooling of the gas. The exact details of these cooling processes are complex and depend on the specific conditions within the gas clouds. But as the gas cooled and gravity continued to pull it together, the density of the gas clouds increased. Eventually, the density reached a critical point, a threshold beyond which the gas cloud could no longer resist the force of gravity. At this point, the gas cloud began to collapse, rapidly accelerating under its own weight. Imagine a giant balloon filled with air. If you slowly let the air out, the balloon will simply deflate. But if you puncture the balloon, the air will rush out in a rapid and explosive burst. Similarly, when a gas cloud reaches a critical density, it undergoes a rapid and catastrophic collapse, triggering the formation of the first stars. But these weren't just any stars. They were the first generation of stars. Population 3 stars, behemoths unlike anything we see today. They were massive, hot, and short-lived, burning through their fuel at an incredible rate. We will soon uncover what secrets these Population 3 stars hold in the continuing drama of the cosmos, but not before considering the expansion of the observable universe. As the gas cooled and gravity continued its relentless work, a profound transition was brewing in the heart of the cosmos. But can you imagine a universe shrouded in complete darkness, where not a single star illuminates the vast expanse of space? This wasn't a temporary eclipse or a fleeting shadow, but an epoch lasting for potentially 100 million years. It was an era that tried the very limits of the imagination. Until, at long last, the universe was poised to ignite the first stars. But what triggered this monumental event? What kind of stars were these cosmic pioneers, and how did they shape the universe we see today? These weren't your average run-of-the-mill stars. These were Population 3 stars, colossal behemoths born from the pristine hydrogen and helium forged in the Big Bang. These stars were absolute giants. Imagine stars hundreds of times more massive than our sun, shining with a ferocious intensity that dwarfs anything we can observe in the modern universe. Why such monstrous sizes? The answer lies in the unique conditions of the early universe. These population 3 stars lacked the heavier elements, the carbon, oxygen, and iron that play a crucial role in star formation today. Without these elements, the primordial gas clouds could not cool as efficiently, leading to the formation of fewer but much larger stars. It's as if the universe in its youth was experimenting with different recipes for star formation, pushing the boundaries of what was possible. These population 3 stars led short but spectacular lives. Burning through their vast reserves of hydrogen at an astounding rate, they shone with an intense blue-white light, illuminating the darkness of the early universe. But their brilliance came at a cost. These stellar giants lived only a few million years, a mere blink of an eye in cosmic terms. Their time was fleeting, but their impact was transformative. Imagine these population 3 stars as cosmic fireworks, exploding in brilliant displays of light and energy. But unlike fireworks here on Earth, these explosions had profound consequences for the evolution of the universe. As these massive stars reached the end of their lives, they detonated as hypernovas, explosions far more powerful than ordinary supernovas. These hypernovas were not only spectacular events, they were also cosmic foundries, forging heavier elements in their fiery cores. Imagine stars as giant alchemists, transforming lighter elements into heavier ones through nuclear fusion. But population 3 stars, with their immense size and energy, could create elements far heavier than those forged in ordinary stars. These hypernova explosions scattered these newly forged elements across the universe, seeding the cosmos with the raw materials for future generations of stars and planets. It was the beginning of cosmic chemical enrichment, a process that would eventually lead to the formation of the diverse and complex universe we observe today. The death of these population 3 stars marked the end of the cosmic dark ages and the dawn of a new era, an era of galaxies, planets, and eventually, life itself. Without these explosions, it is unlikely the universe would exist as it does now. They are the reason why heavier elements exist. It might be reasonable to say that population 3 stars are the most important stars that ever existed. But these population 3 stars remain shrouded in mystery. They existed so long ago that they are incredibly difficult to observe directly. Scientists rely on computer simulations and indirect observations to piece together the puzzle of their existence. What exactly was the average size of a population 3 star? How many of them formed in the early universe? And what role did they play in the ionization of the cosmos, the process by which the universe transitioned from a neutral state to an ionized state? These are just some of the questions that continue to drive research in cosmology. But perhaps, as new telescopes and observational techniques come online, like the James Webb Space Telescope, we will finally catch a glimpse of these elusive cosmic titans, unlocking the secrets of the early universe and gaining a deeper understanding of our own origins. These early pioneers, population 3 stars, may have been the cosmic architects who shaped the foundations of our very existence. But there is still so much more to discover when we begin to look into the formation of galaxies. But these early pioneers, population 3 stars, may have been the cosmic architects who shaped the foundations of our very existence. But their existence was short-lived. What happened to all the materials that they created when they exploded? What forces gathered all of that material together? The death of these population 3 stars marked the end of one era, but it also signaled the dawn of another. Imagine these cosmic explosions, hypernovas of unimaginable scale, scattering gas, dust, and newly forged elements across the vastness of space. This ejected material didn't simply dissipate into the void. Instead, Gravity, the universe's persistent sculptor, began to gather these materials, initiating the construction of the first galaxies. But this process wasn't a tidy, linear progression. Instead, it was a chaotic, messy, and often violent affair, spanning millions upon millions of years. It might be difficult to think of millions of years as quick, but it is a snap of the fingers in cosmic terms. Think of the early universe as a vast construction site where gravity is the foreman, and the raw materials are the gas, dust, and stars left over from the first generation of stars. These materials didn't just magically assemble themselves into galaxies. Instead, they were drawn together by gravity, merging and accreting over vast stretches of time. Imagine countless small streams converging to form a mighty river. In much the same way, small clumps of matter merge to form larger and larger structures, eventually coalescing into protogalaxies, the seeds of future galaxies. But what exactly is a protogalaxy? It's not a fully formed galaxy like our own Milky Way. Instead, it's a nascent structure, a collection of gas, dust, and stars that are still in the process of coming together. Think of it as a cosmic embryo, a structure that contains the potential for a future galaxy, but that has not yet fully developed. The proto-galaxies were turbulent environments, filled with swirling gas, colliding stars, and intense radiation. The conditions were so extreme that they would likely be unrecognizable to us today. And these proto-galaxies weren't isolated entities. They existed within a larger cosmic context, a vast network of filaments and voids known as the cosmic web. Imagine the universe as a giant sponge with dense regions of matter interconnected by thin filaments, separated by vast, empty voids. The galaxies formed along these filaments, drawn together by gravity, like beads on a string. The cosmic web wasn't just a passive backdrop for galaxy formation. It played a crucial role in shaping the structure and evolution of galaxies. The filaments acted as cosmic highways, channeling gas and matter into the proto-galaxies, fueling their growth and development. But what about dark matter? Where does it fit into this picture? Dark matter, that mysterious substance that makes up the majority of the matter in the universe, played a crucial role in the formation of the first galaxies. While we can't see it, its gravitational effects are undeniable. Dark matter acted as a kind of scaffolding, providing the gravitational framework for the formation of galaxies. Think of dark matter as a hidden skeleton, providing the underlying structure for the visible universe. The ordinary matter, the gas, dust, and stars, then accumulated within this dark matter scaffolding, forming the galaxies we observe today. Without dark matter, the galaxies would likely never have formed at all, and the role of dark matter has been confirmed many times even though it cannot be seen. The orbital speeds of many stars could not be explained if it was only the mass of the galaxy that was keeping them in orbit. Something else must be there providing the gravity that keeps these stars in orbit. Mergers and accretion were common occurrences in the early universe. Galaxies were constantly colliding and merging with each other, a process that shaped their size, shape, and composition. These mergers were often violent events, triggering bursts of star formation and transforming the structure of the galaxies. Imagine two galaxies colliding head-on, their stars swirling and colliding, their gas clouds compressed and ignited, and the violence can be hard to imagine. What would it be like to be on a planet in the middle of two galaxies colliding? It would be a light show that would be both spectacular and terrifying. These mergers weren't always destructive. They also provided galaxies with fresh supplies of gas and dust, fueling their growth and star formation. Think of mergers as cosmic recycling events, where galaxies exchange materials, enriching each other and driving their evolution. But how did all of this play out over millions of years? Computer simulations provide invaluable insights into the formation and evolution of galaxies. By modeling the complex interactions between gravity, gas, dust, stars, and dark matter, scientists can recreate the formation of galaxies in a virtual universe. These simulations reveal the intricate processes that shaped the first galaxies, showing how they grew, merged, and evolved over vast stretches of time. But these simulations are only as good as the data that is put in them, and that data can change rapidly as our tools continue to improve. These simulations are a work in progress. Imagine a time-lapse movie of the early universe showing the formation of the first galaxies in fast forward. You would see gas clouds collapsing, stars igniting, galaxies merging, and the cosmic web evolving over millions of years. It would be a spectacular display of cosmic evolution. And so, from the ashes of the first stars, the building blocks of galaxies began to assemble, shaped by gravity, sculpted by dark matter, and fueled by mergers and accretion. These early proto-galaxies were the seeds of the universe we see today, the precursors to the magnificent spiral and elliptical galaxies that populate the cosmos. But how do we observe these distant galaxies? How do we peer back in time to witness the formation of the first structures in the universe? Edwin Hubble helped us answer that question. From these cosmic architects, the population 3 stars, rose the building blocks for what would become galaxies. But how can one possibly observe these objects so far away and so long ago? Consider that the faintest glimmers of these primordial structures reach us after traveling for 13 billion years. How does one even begin to fathom such distances, such unimaginable stretches of time? The answer, perhaps surprisingly, lies in a phenomenon known as redshift, and the groundbreaking observations of one man, Edwin Hubble. Imagine an astronomer perched atop Mount Wilson in California in the 1920s, meticulously observing distant galaxies through what was then the world's largest telescope. Edwin Hubble wasn't just cataloging these galaxies. He was measuring their distances and their speeds, and what he discovered would forever change our understanding of the universe. Hubble noticed something peculiar about the light coming from these galaxies. It was shifted towards the red end of the spectrum. Now, what does it mean for light to be redshifted? Think of it as a cosmic Doppler effect. You have probably experienced the Doppler effect with sound. When a car approaches you, its sound is higher pitched, and then when it drives past you, the sound goes down. Imagine the sound is light, and the car is a star. Just as the sound of a car changes as it moves relative to you, the light from a star or galaxy will change depending on its motion relative to us. If a galaxy is moving away from us, its light waves are stretched, shifting them towards the red end of the spectrum. If a galaxy is moving towards us, its light waves are compressed, shifting them towards the blue end of the spectrum. This is known as blue shift. Now here's the mind-blowing part. Hubble discovered that almost all the galaxies he observed were redshifted, meaning they were all moving away from us. And not only were they moving away from us, but the farther away a galaxy was, the faster it was receding. It's as if the universe was a giant loaf of raisin bread baking in an oven, and the galaxies were the raisins. As the bread expands, the raisins move farther apart, and the farther apart 2 raisins are, the faster they move away from each other. Hubble's discovery, published in 1929, was a watershed moment in the history of cosmology. It provided the first major observational support for the Big Bang theory, the idea that the universe began as an incredibly hot, dense state and has been expanding ever since. Hubble's observations revealed that the universe wasn't static and unchanging, as many scientists had previously believed. Instead, it was dynamic, evolving, and above all, expanding. Perhaps you are wondering to yourself, was Hubble the first person to notice this redshift? Astronomers had observed redshift previously, but it was Hubble who connected the dots, realizing that this redshift was related to the distance of the galaxies, and that it implied the expansion of the universe. This realization sent shockwaves through the scientific community. It challenged long-held assumptions and opened up a whole new realm of possibilities. Imagine the thrill of discovering that the universe itself is stretching, growing larger and larger with each passing moment. Some have asked, what if the Earth is just at the center of the universe and everything is moving away from it? That is an astute observation, but it is not the case. No matter where you are in the universe, everything would appear to be moving away from you. If you were on a different galaxy, it would look like that galaxy was the center of the universe. Think of it this way. It is not just the galaxies that are moving away from each other, it is space itself that is expanding. But Hubble's discovery wasn't just about galaxies moving away from us. It was about something far more profound. It was about the nature of space and time itself. It was about the realization that the universe is not a static container, but a dynamic entity that is constantly evolving. Hubble's discovery changed our place in the universe. The Earth is not special, and neither is our galaxy. Everything is moving away from everything else. He provided a revolutionary perspective that the observable universe is vast and everything is in motion. Hubble's initial observations were groundbreaking. He looked at 24 galaxies to make his initial observations. But that's just a small percentage of the observable universe. And astronomers continue to confirm Hubble's findings as new observation methods and better telescopes become available. What Hubble did provides us a way to measure the expansion rate of the universe, a value known as the Hubble constant. The Hubble constant tells us how fast the universe is expanding at the present time. It's a fundamental parameter in cosmology, and knowing its value is essential for understanding the age, size, and ultimate fate of the cosmos. But determining the Hubble constant has proven to be surprisingly challenging. Different methods of measurement yield slightly different results, leading to what is known as the Hubble tension. Some measurements, based on the cosmic microwave background, suggest a lower value for the Hubble constant, while other measurements, based on observations of nearby supernovae, suggest a higher value. This discrepancy has sparked a debate among cosmologists, with some suggesting that it could be a sign of new physics beyond the standard model. What if our understanding of dark energy is wrong? What if there are new particles or forces at play that we haven't yet discovered? The Hubble tension remains one of the biggest mysteries in cosmology today, a challenge that could potentially lead to a revolution in our understanding of the universe. Hubble's discovery of the expanding universe was a pivotal moment in our quest to understand the cosmos. It provided the first major observational support for the Big Bang theory. But is the redshift the only evidence we have for the Big Bang? What other clues can we find that support this revolutionary idea? Perhaps we can begin to further examine what the light elements that we talked about earlier have to say. Hubble's discovery of the expanding universe was a pivotal moment in our quest to understand the cosmos. It provided the first major observational support for the Big Bang theory. But is the redshift the only evidence we have for the Big Bang? What other clues can we find that support this revolutionary idea? Prepare to have your mind blown because the answer is written in the stars themselves, or rather, in the precise amounts of certain light elements scattered throughout the universe. Think of it as a cosmic recipe card, detailing the ingredients and proportions needed to bake a universe. Big Bang nucleosynthesis, or BBN, predicts the abundance of light elements like hydrogen, helium, and lithium that should have been created in the first few minutes after the Big Bang. It's a bold claim, but one that's been tested and confirmed with remarkable accuracy. But what makes it so precise? Imagine the early universe as the ultimate pressure cooker, where protons and neutrons fuse together in a furious dance of nuclear reactions. The temperature and density were so extreme that the formation of heavier elements was quickly snuffed out. This primordial alchemy left behind a unique elemental fingerprint, a specific ratio of hydrogen, helium, and lithium that should be present throughout the cosmos. But how can we possibly measure these primordial abundances? We can't just go out and collect samples of the early universe. The answer lies in studying the oldest, most pristine objects we can find, distant gas clouds, ancient stars, and even the atmospheres of some planets. The most commonly used method is by using absorption spectra, or when the light of a background star passes through a cloud, the elements in that cloud will absorb that light. The elements then make a signature dark line in the spectrum. These cosmic relics offer a window into the past, allowing us to glimpse the elemental composition of the universe shortly after the Big Bang. Now, brace yourselves for a cosmic coincidence that will make you question everything you thought you knew. The observed amounts of hydrogen, helium, and lithium in these ancient objects match the predictions of Big Bang nucleosynthesis with uncanny precision. It's like finding a perfectly preserved fossil, confirming a long-held theory with undeniable evidence. This agreement is one of the strongest pillars supporting the Big Bang model, a testament to the power of scientific prediction and observation. This is all possible using the power of math. Calculations and equations have provided a strong model for the Big Bang theory to stand on. The abundance of helium is a particularly compelling piece of evidence. Helium is produced in stars, but the amount of helium we observe in the oldest objects is far greater than what could have been created by stellar processes alone. This excess helium is a direct remnant of Big Bang nucleosynthesis, a cosmic signature that points directly back to the early universe. But even with all of this evidence, there are still some mysteries surrounding the primordial abundances. The observed amount of lithium-7, one of the isotopes of lithium, is about a factor of 2 or 3 lower than what is predicted by Big Bang nucleosynthesis. This discrepancy, known as the lithium problem, has baffled scientists for decades. Is it a sign that our understanding of Big Bang nucleosynthesis is incomplete? Are there unknown processes at play that are destroying lithium in the early universe? Or is it simply a problem with our measurements? The lithium problem remains an active area of research, and scientists are constantly developing new techniques to measure the primordial abundance of lithium with greater accuracy. But how do we account for the heavier elements like carbon, oxygen, and iron that are essential for life as we know it? If Big Bang nucleosynthesis only produced light elements, where did all the heavier stuff come from? It's a question that takes us back to the heart of stars, those cosmic furnaces that forge heavier elements in their fiery cores. Now we look to the missing mass that we know is all around us. But how do we account for the heavier elements like carbon, oxygen, and iron that are essential for life as we know it? If Big Bang nucleosynthesis only produced light elements, where did all the heavier stuff come from? It's a question that takes us back to the heart of stars, those cosmic furnaces that forge heavier elements in their fiery cores. But even with the life-giving energy of the stars, it turns out that something still doesn't quite add up. You see, when astronomers began to carefully measure the masses of galaxies and how fast they were spinning, they stumbled upon a cosmic accounting problem. A problem so profound it would rewrite our understanding of the universe. Imagine observing a spinning figure skater. If you know how fast they are spinning and you can estimate their mass, you can predict how fast they should be moving at the edge of their spin. But what if the skater was spinning way too fast for their known mass? What if they should be flying apart, but they are somehow holding together? You might suspect there is something missing. Some hidden weight that is keeping them grounded. This is precisely the situation that astronomers encountered when they looked at galaxies. Galaxies are spinning, vast collections of stars, gas, and dust rotating around a central point. By measuring the speed at which stars are orbiting, astronomers can estimate the galaxy's mass, the amount of matter that is pulling everything together. But when they did the math, something didn't add up. The galaxies were spinning much faster than they should have been, based on the amount of visible matter they contained. They should have been flying apart, but they weren't. It was like the universe was playing a trick on us, hiding something in plain sight. There had to be something else out there, something invisible, that was providing the extra gravity needed to hold these galaxies together. This invisible something became known as dark matter, a name that perfectly captures its mysterious nature. It's matter because it has gravity, but it's dark because it doesn't interact with light. We can't see it, we can't touch it, we can't even detect it directly. But if we can't see it, how do we know it's there? The evidence for dark matter is overwhelming, coming from a variety of different sources. One of the strongest lines of evidence comes from gravitational lensing. Imagine a massive object, like a galaxy, or a galaxy cluster, sitting in front of a more distant galaxy. The gravity of the massive object will bend the light from the distant galaxy, distorting its image and creating multiple images. This is similar to how a lens bends light, magnifying and distorting the image of an object behind it. The amount of bending depends on the mass of the lensing object. Astronomers have observed gravitational lensing around many galaxy clusters, and when they measured the amount of bending, they found that it was far greater than what could be accounted for by the visible matter in the cluster. Once again, there had to be something else there, something invisible that was contributing to the gravity. Dark matter. But wait, there is more. Another piece of evidence comes from observations of galaxy clusters, the largest known structures in the universe. These clusters are held together by gravity, and they contain hot gas that emits X-rays. By measuring the temperature and brightness of this X-ray emitting gas, astronomers can estimate the total mass of the cluster. And once again they find that the mass of the visible matter is not enough to hold the cluster together. Dark matter is needed to provide the extra gravity. So what exactly is this dark matter? What is it made of? That is one of the biggest mysteries in modern physics. Scientists have proposed many different candidates for dark matter, ranging from hypothetical particles to more exotic objects. One of the leading candidates is something called a weakly interacting massive particle, or WIMP. Imagine a particle that interacts with ordinary matter only through the weak nuclear force and gravity. This would make it very difficult to detect directly, as it would rarely interact with our detectors. But WIMPs would still have mass, and therefore would interact gravitationally, explaining the observed effects of dark matter. Another candidate is something called an axion, an extremely light particle that was originally proposed to solve another problem in particle physics. Axions are predicted to interact very weakly with ordinary matter, making them extremely difficult to detect, but they are also thought to be very numerous, potentially making up a significant fraction of the dark matter in the universe. And just how much dark matter is out there? Current estimates suggest that dark matter makes up about 27% of the total mass energy content of the universe. That is more than 5 times the amount of ordinary matter, the stuff that makes up stars, planets, and us. Ordinary matter only accounts for about 5% of the universe. The rest is dark energy, which accounts for approximately 68% of the universe's makeup. So not only is dark matter invisible, it's also far more abundant than ordinary matter. But the search for dark matter is not just about understanding the composition of the universe. It's also about understanding how the universe evolved. Dark matter plays a crucial role in the formation of galaxies and large-scale structures. Computer simulations have shown that without dark matter, the universe would look very different. Galaxies would be smaller, less numerous, and more spread out. It's as if dark matter is the scaffolding upon which the visible universe is built. It provides the gravitational framework that allows galaxies to form and evolve. Now, scientists are working hard to discover dark matter by building extremely sensitive detectors that are shielded from all sorts of radiation. These instruments cost millions upon millions of dollars, and it is still unknown when they will be able to find dark matter. The search goes on, and the cosmos continues to reveal its secrets. But even with dark matter accounting for a significant portion of the universe's mass energy content, another even stranger force is at play, accelerating the expansion of the cosmos at an ever-increasing rate. What could this be? But even with dark matter accounting for a significant portion of the universe's mass energy content, another even stranger force is at play, accelerating the expansion of the cosmos at an ever-increasing rate. What could this be? Are we talking about a cosmic prank? A universal push? A force so subtle, so pervasive that it's been hiding in plain sight for billions of years? Imagine, if you will, a balloon being inflated not just steadily, but faster and faster with each passing moment. That's the universe we inhabit, a cosmos whose expansion is not slowing down as one might expect, but accelerating. defying gravity's pull. For decades, scientists assumed that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down due to the gravitational attraction of all the matter within it. It seemed intuitive, a cosmic law of attraction writ large. But in 1998, two independent teams of astronomers led by Saul Perlmutter, Brian Schmidt, and Adam Rees made a startling discovery that shook the foundations of cosmology. They were studying distant supernovae, those spectacular stellar explosions that can outshine entire galaxies, to measure the rate of the universe's expansion over time. These weren't just any supernovae. These were Type 1a supernovae, which serve as what astronomers call standard candles. Think of them as light bulbs with a known wattage. By measuring their apparent brightness, we can calculate their distance. These astronomers used these cosmic mile markers to chart the universe's expansion history. But what they found was not what they expected. The supernovae were fainter than they should have been, indicating that they were farther away than predicted. This meant that the universe's expansion was not slowing down but accelerating. It was a discovery so unexpected, so revolutionary, that it earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. It was like discovering that your car, instead of slowing down when you take your foot off the gas, is actually speeding up, seemingly defying the laws of physics. What could be causing this cosmic acceleration? What mysterious force could be pushing the universe apart? The answer, as far as we know, is something called dark energy, a name that speaks volumes about our ignorance of its true nature. We know it's there, we can see its effects, but we have no idea what it actually is. Imagine a universe filled with a mysterious, invisible fluid, permeating all of space, exerting a negative pressure that pushes everything apart. That's one way to think about dark energy. Unlike ordinary matter, which exerts a gravitational pull that attracts things together, dark energy exerts a repulsive force that pushes things apart. It's like a cosmic anti-gravity, a force that counteracts the pull of gravity on the largest scales. Perhaps you are asking yourself, is this dark energy just Einstein's cosmological constant that he dismissed? It is an interesting thought, and it has crossed the minds of many scientists. Einstein originally introduced this into his equations of general relativity to create a static, non-expanding universe. However, after Hubble discovered the expansion of the universe, Einstein called it the biggest blunder of his career. That may not have been the case at all, and dark energy might be related. But what exactly is dark energy? That's the million, or rather the trillion-dollar question that cosmologists are still trying to answer. One possibility is that dark energy is simply the energy of empty space, a kind of vacuum energy that arises from quantum fluctuations. According to quantum mechanics, even empty space is not truly empty. It's filled with virtual particles that are constantly popping into and out of existence, creating a kind of background energy. Another possibility is that dark energy is a new kind of fundamental field, similar to the electromagnetic field or the gravitational field. This field, sometimes called quintessence, would have a negative pressure, causing the universe to accelerate. Yet another possibility is that our understanding of gravity is incomplete, and that dark energy is not a real thing at all, but rather a manifestation of our flawed understanding of general relativity on the largest scales. The implications of dark energy for the ultimate fate of the cosmos are profound. If dark energy continues to dominate the universe, as it seems to be doing now, the universe will continue to expand at an ever-increasing rate. This could lead to what is known as the Big Freeze, where the universe becomes increasingly cold and empty as galaxies move farther and farther apart. Eventually, star formation will cease, and the universe will fade into darkness. Another possibility is the Big Rip, a scenario where the expansion of the universe accelerates so rapidly that it eventually tears apart all structures, from galaxies to stars to atoms. In this scenario, the universe would end in a violent and cataclysmic explosion. Or is this all there is to the universe? Are there new surprises out there? The quest for the truth continues. But what could this be? Are we talking about a cosmic prank? A universal push? A force so subtle, so pervasive that it's been hiding in plain sight for billions of years? So we have the expansion of the universe, a recipe of light elements, the presence of dark matter, and the perplexing nature of dark energy. But how do we assemble all of these seemingly disparate pieces into a coherent picture of the cosmos? Is there a single model that can explain all of these observations, a unifying framework that can make sense of the universe's origin, evolution, and ultimate fate? The answer, according to most cosmologists, is yes, and it's called the lambda cold dark matter model, often abbreviated as lambda CDM. It is the current standard model of cosmology, our best attempt to describe the universe's evolution from the Big Bang to the present day. But what exactly is this lambda CDM model? What are its key ingredients, and how well does it stand up to the scrutiny of observation and experiment? First, let's break down the name. The lambda refers to the cosmological constant, a term that represents dark energy, the mysterious force that is accelerating the expansion of the universe. The CDM refers to cold dark matter, the invisible substance that makes up the majority of the matter in the universe. So, the lambda CDM model is a framework that combines dark energy, cold dark matter, ordinary matter, radiation, and the Big Bang theory into a single, coherent picture of the cosmos. It's like a cosmic jigsaw puzzle, where each piece represents a different component of the universe, and the lambda CDM model is the instruction manual that tells us how to put it all together. At its heart, the lambda CDM model is based on Einstein's theory of general relativity, which describes how gravity works on the largest scales. General relativity tells us that the universe is dynamic, constantly evolving under the influence of gravity and energy. But general relativity alone is not enough to explain all of the observations we make about the universe. We also need to invoke dark energy and dark matter, two mysterious components that we don't fully understand. The lambda CDM model describes a universe that began with the Big Bang, an incredibly hot, dense state that expanded and cooled over billions of years. As the universe expanded, it underwent a series of phase transitions, leading to the formation of protons, neutrons, atoms, stars, galaxies, and eventually, us. But the lambda CDM model is not just a theoretical construct. It has been tested and confirmed by a wide range of observations, from the cosmic microwave background to the distribution of galaxies in the universe. Perhaps you are wondering, how does this all fit together? It is a fair question that many scientists have spent their careers answering. For instance, the lambda CDM model accurately predicts the temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang. These fluctuations, only a few millionths of a degree Celsius in magnitude, are the seeds of future galaxies, the regions of slightly higher density that would eventually collapse under gravity to form the structures we observe today. The lambda CDM model also accurately predicts the large-scale structure of the universe, the vast network of filaments and voids that connects galaxies across billions of light years. Computer simulations based on the lambda CDM model have successfully recreated the cosmic web, showing how galaxies form and evolve within this intricate structure. The lambda CDM model can also explain the observed abundance of light elements in the universe, such as hydrogen, helium, and lithium. The model's predictions for these primordial abundances agree remarkably well with observations, providing further evidence for the Big Bang theory and the lambda CDM framework. But despite its successes, the lambda CDM model is not without its challenges. There are still some puzzles that it cannot fully explain, some mysteries that continue to baffle scientists. For example, the model predicts a certain number of small galaxies orbiting our own Milky Way, but observations have revealed far fewer than expected. This is known as the missing satellites problem. Then there is the Hubble tension. Different methods of measuring the universe's expansion rate yield different results. Another challenge is the nature of dark matter and dark energy. We know they are there, we can see their effects, but we don't know what they actually are. Are they fundamental particles, new fields, or something else entirely? These questions continue to drive research in cosmology and particle physics. Even with these known unknowns, the lambda CDM model is the best picture we have of the universe. It's a framework that has been tested and confirmed by a wide range of observations, providing a coherent and consistent description of the cosmos. But it's not the final word. Science is a process of continuous refinement, and the lambda CDM model is constantly being challenged and updated as new data becomes available. What about the alternatives? There are some alternative theories out there, but none of them provide such a strong base that the lambda CDM model has provided. There are theories like Mondi modified Newtonian dynamics that attempt to describe galactic rotation curves without dark matter. But there are issues with these models when explaining the universe on a larger scale. It is worth noting that these theories are not disproven. Some of the greatest minds in cosmology are looking for improvements to the lambda CDM model. Are there small changes to our fundamental understanding of gravity? That is yet to be determined. Perhaps, as we continue to probe the universe with ever more powerful telescopes and detectors, we will uncover new clues that will lead us to a deeper understanding of dark energy, dark matter, and the ultimate fate of the cosmos. It is thanks to the technological advancements made, like the incredible telescopes we can use, that cosmology has grown so much in the past 100 years. They provide a peek into the past and a glimmer of hope for what the future holds. But how do we even know these dark and bright mysteries are out there? How have humans uncovered the secrets of a universe so vast and ancient? The truth is out there, and we have built the eyes to see it. Imagine trying to understand the entirety of the ocean using only a bucket and a rope. That, in essence, was the challenge facing early astronomers. But with ingenuity, relentless curiosity, and ever-advancing technology, we have crafted increasingly powerful tools to probe the cosmos, telescopes that have pierced the veil of distance and time itself. From humble beginnings, gazing at the night sky with the naked eye, to sophisticated instruments orbiting the Earth, our ability to observe the universe has undergone a revolution. It began with simple lenses, ground and polished with painstaking care, allowing early observers like Galileo Galilei to glimpse the moons of Jupiter and the rings of Saturn for the first time. These early telescopes, though rudimentary by today's standards, opened up a new world of wonder, challenging long-held beliefs and sparking a scientific revolution. It was like discovering a hidden continent, teeming with unknown life and landscapes. What would Galileo think of the technology used today? But ground-based telescopes are limited, constrained by the Earth's atmosphere, a swirling blanket of air that distorts and absorbs some of the light from the heavens. Think of it as trying to see through a shimmering heat haze, or trying to stargaze on a cloudy day. This is where space-based telescopes come in. By launching telescopes into orbit above the Earth's atmosphere, we can obtain images and data of unparalleled clarity and precision. The Hubble Space Telescope, launched in 1990, is perhaps the most iconic example of a space-based observatory. Named after Edwin Hubble, the astronomer who discovered the expanding universe, this telescope has revolutionized our understanding of the cosmos, providing breathtaking images of galaxies, nebulae, and other celestial objects. It is hard to imagine that it was launched with a flaw that had to be corrected by astronauts on a space mission. What would have happened if that flaw had not been fixed? We might not have the beautiful images that we have of space today. But Hubble is not just a pretty picture machine. It's also a powerful scientific instrument, equipped with a suite of detectors that can observe light across a wide range of wavelengths, from the ultraviolet to the near-infrared. But there is only so much you can do from a certain location. So, what is the next step for astronomers? The James Webb Space Telescope has been designed to take over where Hubble left off. Why observe in different wavelengths? It's because different wavelengths of light reveal different aspects of the universe. Visible light, the kind of light that our eyes can see, is only a small fraction of the electromagnetic spectrum. There is also infrared light, which is longer wavelength than visible light, ultraviolet light, which is shorter wavelength than visible light, as well as radio waves, microwaves, X-rays, and gamma rays. Each of these wavelengths provides a unique window into the cosmos. For example, infrared light can penetrate through clouds of dust and gas, allowing us to see objects that are hidden in visible light. Ultraviolet light can reveal the hot, energetic regions of galaxies. X-rays can probe the extreme environments around black holes and neutron stars. Radio waves can map the distribution of hydrogen gas in the universe. Think of it as having different senses. If you only used your eyes to understand the world, you would not be able to hear a car coming up behind you. Each of the spectrums of light give us more data to understand the universe. The James Webb Space Telescope, launched in 2021, is the most powerful space telescope ever built. It is designed to observe the universe in the infrared, allowing it to see the first stars and galaxies that formed after the Big Bang. Imagine peering back in time, witnessing the birth of the cosmos. What mysteries are hidden in this primordial light? But building these incredible instruments is no easy task. It requires pushing the boundaries of technology, developing new materials, and overcoming countless engineering challenges. The mirrors of the James Webb Space Telescope, for example, are made of beryllium, a lightweight and strong metal that is coated with gold to enhance its reflectivity. The mirrors had to be folded up to fit inside the rocket. They were then unfolded in space. What an amazing piece of engineering. And the detectors on these telescopes are incredibly sensitive, capable of detecting the faintest glimmers of light from the most distant objects in the universe. The technological advancements required to build these telescopes are truly astonishing, a testament to human ingenuity and perseverance. But these powerful telescopes, whether ground-based or space-based, are just tools. It's the scientists, engineers, and technicians who use these tools to make groundbreaking discoveries. They are the ones who design the experiments, collect the data, and interpret the results. It's a collaborative effort involving people from all over the world working together to unravel the mysteries of the cosmos. From the first simple lenses to the sophisticated instruments of today, our quest to understand the universe has driven technological innovation and expanded the horizons of human knowledge. As we continue to build ever more powerful telescopes, we can expect even more surprising revelations about our place in the cosmos. These tools gather the light from the distant past, but there might be other ways to look into the past. Perhaps we are only scratching the surface of cosmic discovery. Are there cracks in the foundation that are yet to be discovered? But are there cracks in this seemingly airtight explanation of the cosmos? Has the universe thrown us a curveball, hinting at a reality more complex than we can currently grasp? The Lambda CDM model, for all its successes, isn't without its nagging questions and unresolved issues, like a detective meticulously examining a crime scene. Cosmologists are constantly searching for inconsistencies, anomalies, anything that might suggest a flaw in the prevailing theory. One of the most persistent challenges is known as the horizon problem. Imagine peering out into the night sky, looking at the cosmic microwave background, the afterglow of the Big Bang. This radiation is remarkably uniform in temperature, almost perfectly the same in every direction. But here's the puzzle. Regions of the CMB on opposite sides of the sky are so far apart that they could never have been in causal contact in the early universe. They could never have exchanged information, never have reached a state of thermal equilibrium. So how did they end up having the same temperature? It's as if two people living on opposite sides of the planet woke up one morning wearing the exact same outfit without ever having spoken to each other. Inflation, that period of rapid expansion in the early universe, offers a potential solution. By stretching the universe to an enormous size in a tiny fraction of a second, Inflation could have brought all regions into causal contact before they were separated by the expansion. But inflation itself is not without its own set of questions. What exactly caused inflation to start and stop? What was the nature of the inflaton field that drove this rapid expansion? These are questions that continue to baffle physicists. Another persistent headache for cosmologists is the flatness problem. The universe appears to be remarkably flat, meaning that its geometry is very close to Euclidean geometry, the kind of geometry we learn in high school. But according to general relativity, the universe could have been curved either positively like a sphere or negatively like a saddle. The fact that it's so close to being flat requires an incredibly fine-tuned set of initial conditions. It's like balancing a pencil on its tip. It's possible, but it requires an extraordinary amount of precision. Inflation also offers a potential solution to the flatness problem. By stretching out any initial curvature, inflation could have made the universe appear much flatter than it actually is. It is similar to taking a deflated balloon with wrinkles on it, then blowing it up. The wrinkles will get stretched out and look flat. Then there are the mysteries of dark matter and dark energy, those invisible components that make up the vast majority of the universe. We know they are there, we can see their gravitational effects, but we have no idea what they actually are. It's like discovering that your house is being supported by invisible pillars. You know they are there because the house is still standing, but you can't see them, you can't touch them, you can't even detect them directly. Are dark matter and dark energy fundamental particles, new fields, or something else entirely? The search for answers to these questions is one of the most active areas of research in cosmology and particle physics. Perhaps these mysteries will lead us to a deeper understanding of the universe, or perhaps they will lead us down a path of new revelations. Given these challenges, it's natural to ask whether there are alternative cosmological models that might offer a better explanation of the universe. Over the years, scientists have proposed a number of alternative theories, some of which challenge the fundamental assumptions of the Big Bang model. One example is modified Newtonian dynamics, or MOND, which attempts to explain the rotation curves of galaxies without invoking dark matter. MOND proposes that gravity behaves differently at very low accelerations than what is predicted by Newton's law of gravity. While MOND can successfully explain the rotation curves of some galaxies, it has difficulty explaining other observations, such as the cosmic microwave background and the large-scale structure of the universe. Another alternative theory is the ekpyrotic universe, which proposes that the Big Bang was not the beginning of the universe, but rather a transition from a pre-existing phase of contraction. In the ekpyrotic scenario, the universe undergoes a period of slow contraction, followed by a bounce that triggers the expansion we observe today. These are interesting and are worthy of investigation, but science thrives on questioning and testing established theories. It's a process of constant refinement, where new data and new ideas are constantly challenging our understanding of the universe. Perhaps a new revolution in cosmology is needed, a paradigm shift that will transform our understanding of the cosmos. Or perhaps the lambda CDM model will continue to evolve, incorporating new discoveries and refining its predictions. Could it be that the universe has more stories to tell, and are we on the verge of a new revelation? Even as we refine our understanding of the cosmos through observation and complex mathematics, there is a nagging question that remains. What happened at the very beginning? What were the conditions at the instant of creation, when the universe was smaller than an atom and hotter than any star? It's a realm where the familiar laws of physics break down, where our understanding of space and time becomes fuzzy, and where we must confront the most profound mysteries of existence. Consider the two pillars of modern physics, general relativity and quantum mechanics. General relativity, Einstein's masterpiece, describes gravity as a curvature of space-time, a cosmic dance between mass and energy. It works beautifully on large scales, explaining the orbits of planets, the bending of light around black holes, and the expansion of the universe. Quantum mechanics, on the other hand, describes the behavior of matter and energy at the atomic and subatomic level. It's a world of probabilities, uncertainties, and bizarre phenomena like quantum entanglement and superposition. It also works beautifully on small scales. But when we try to apply both quantum mechanics and general relativity to the very first moments of the universe, we run into a problem. The equations simply don't work. They produce infinities, singularities, and other mathematical absurdities. It's as if the universe is telling us that we are missing a crucial piece of the puzzle. The problem is that general relativity treats space-time as a smooth, continuous fabric, while quantum mechanics tells us that, at the smallest scales, space-time is likely grainy and quantized. Imagine trying to describe the surface of the ocean using only the equations of smooth fluid dynamics, ignoring the fact that the ocean is made up of individual water molecules. At large scales, the smooth approximation works well, but at the smallest scales, you need to take into account the discrete nature of water. Similarly, to understand the very first moments of the universe, we need a theory of quantum gravity, a theory that can reconcile general relativity with quantum mechanics. Such a theory would describe gravity not as a smooth curvature of space-time, but as a force mediated by quantum particles, much like the other fundamental forces of nature. But developing a theory of quantum gravity has proven to be one of the greatest challenges in theoretical physics. Despite decades of effort, scientists have yet to come up with a complete and consistent theory. There are, however, some promising candidates. One of the leading contenders is string theory. String theory proposes that fundamental particles are not point-like, but rather tiny, vibrating strings. These strings exist in 10 dimensions, 3 spatial dimensions, 1 time dimension, and 6 extra dimensions that are curled up and hidden from our everyday perception. Imagine the universe is not made of individual grains of sand, but instead an intricate tapestry woven from countless shimmering threads. These strings can vibrate in different ways, giving rise to different particles with different masses and charges. String theory is not only a theory of quantum gravity, but also a theory of everything, attempting to unify all the fundamental forces of nature into a single, elegant framework. Another contender is loop quantum gravity. Loop quantum gravity takes a different approach, quantizing space-time itself. According to loop quantum gravity, space-time is not a smooth, continuous fabric, but rather a network of interconnected loops. These loops are the fundamental building blocks of space-time, and they are quantized, meaning that they come in discrete units, like pixels on a screen. Imagine space is not a smooth, continuous fabric, but rather a mosaic of tiny, indivisible tiles. At the very beginning, quantum fluctuations could have played a critical role in seeding cosmic structure. Quantum fluctuations are tiny, random variations in energy that arise from the uncertainty principle of quantum mechanics. These fluctuations are normally so small that they are undetectable, but in the incredibly dense and energetic environment of the early universe, they could have been amplified by gravity, growing into the seeds of future galaxies and large-scale structures. Think of it as a cosmic lottery, where quantum fluctuations are the winning tickets. Some regions of space ended up with slightly more energy than others, and these over dense regions attracted more and more matter over time, eventually collapsing to form galaxies and clusters of galaxies. It is the ultimate question that scientists are asking. How did the universe emerge from nothing? It's a question that has haunted philosophers and scientists for centuries, and it continues to drive research in theoretical physics. How can something so complex and diverse arise from a state of nothingness? Perhaps, in understanding the very origin of our universe, we've only been granted a glimpse of something far grander. Like explorers charting a vast ocean, are we mistaking our own island for the entirety of the world? What if our universe, with its billions of galaxies and unfathomable expanse, is just one of countless others, existing within a larger multiverse? The idea might sound like science fiction, something straight out of a Philip K. Dick novel, but the multiverse is actually a concept being explored by some of the most brilliant minds in physics. It's not just wild speculation, it's a possibility that arises from some of our most successful, yet mind-bending theories about the universe. Theories like eternal inflation. Remember inflation? That period of hyper-accelerated expansion in the early universe? Well, some physicists believe that inflation never actually stopped. Instead, it continues eternally, creating an infinite number of bubble universes, each with its own unique set of physical laws and constants. Think of it like a cosmic bubble bath, where new universes are constantly popping into existence, each one a separate reality, distinct from our own. In this scenario, our universe is just one bubble in a vast, ever-expanding multiverse. We might never be able to travel to these other universes, or even detect them directly. They are simply too far away, separated from us by an infinite gulf of space-time, but their existence, if it's real, would have profound implications for our understanding of the universe. It could explain why the physical constants in our universe are so finely tuned for life. If there are countless other universes with different constants, it's perhaps not surprising that we find ourselves in one that is hospitable to life. It would be like winning the cosmic lottery. Then there is the landscape of string theory. String theory, as you might recall, suggests that fundamental particles are not point-like but rather tiny, vibrating strings. These strings exist in 10 dimensions, most of which are curled up and hidden from our everyday perception. But here's the kicker. String theory predicts that there are roughly 10 to the power of 500 different ways to curl up these extra dimensions, each one corresponding to a different universe with different physical laws. 10 to the power of 500 is a number so large that it is virtually impossible to comprehend. It's far more than the number of atoms in the observable universe. This vast collection of possible universes is known as the string theory landscape. Imagine a mountain range with countless peaks and valleys, each one representing a different universe with different properties. Our universe would be just one tiny peak in this vast landscape. Could it be that other universes could exist with different laws? What if gravity was stronger or weaker in another universe? What if the speed of light was different? What if there were different types of particles that don't exist in our universe? The possibilities are endless. It makes you wonder what it would be like to visit one of these other universes. And what about the philosophical implications of the multiverse? If our universe is just one of many, does that diminish our significance? Does it mean that our existence is just a cosmic accident, a random occurrence in an infinite sea of possibilities? Or does it perhaps suggest that there is a deeper, more fundamental reality underlying it all, a reality that we are only beginning to glimpse? These are questions that have been debated by philosophers and theologians for centuries. The existence of a multiverse could also challenge our understanding of free will. If there are countless other versions of us living in other universes making different choices, does that mean that our choices are predetermined? Or do we have genuine agency, the ability to shape our own destiny? Some have proposed the idea that quantum mechanics might come into play. Hugh Everett came up with the many worlds interpretation. Every quantum decision that is made causes a split of the universe into new universes. Of course, the multiverse is a highly speculative idea. There is currently no direct evidence to support its existence, and it may never be possible to test the idea directly. How could we ever hope to travel to another universe or even detect one from afar? But that doesn't mean that the multiverse is not a valid scientific concept. Scientists can test the implications of these ideas. The multiverse might impact our universe in very subtle ways. Even if we can never prove the existence of a multiverse, exploring the possibility can help us to better understand our own universe. It can challenge our assumptions, force us to think outside the box, and open up new avenues of research. It is also important to keep an open mind. Sometimes the ideas that seem the craziest actually turn out to be true. Pondering our place in a potentially infinite cosmic sea is a humbling experience. It reminds us that we are just a small part of a much larger reality, a reality that is far more complex and mysterious than we can currently imagine. It is a challenge for the bold, and a concept that will continue to drive scientific and philosophical inquiry for generations to come. Even as we ponder the vastness of the multiverse and our place within it, a far more immediate question looms. What is the ultimate fate of our own universe? Is it destined to expand forever, growing colder and emptier with each passing eon? Will it be torn apart by the relentless force of dark energy? Or could it perhaps collapse in on itself, returning to the very singularity from which it was born? The answer, it turns out, is intimately connected to the universe's beginning, a cosmic echo that resonates through billions upon billions of years. Imagine a cosmic game of tug-of-war, where gravity is pulling inward, trying to slow down the expansion set in motion by the Big Bang, and dark energy is pulling outward, accelerating the expansion at an ever-increasing rate. The winner of this cosmic tug-of-war will determine the ultimate fate of the universe. So what are the possible outcomes? What are the scenarios that await us in the unimaginably distant future? One possibility, perhaps the most widely discussed, is the Big Freeze. In this scenario, dark energy continues to dominate, driving the universe to expand at an ever-increasing rate. Galaxies move farther and farther apart, eventually becoming so distant that they are no longer visible to each other. Star formation gradually ceases, as the gas and dust needed to create new stars is used up. The universe becomes increasingly cold and empty, a vast, dark void with only the faintest whispers of light. Picture a cosmic winter where everything is slowly but surely freezing to death. Stars burn out, galaxies fade away, and the universe becomes an increasingly desolate and lonely place. Eventually, even black holes will evaporate, radiating away their mass through Hawking radiation, leaving nothing but the faint glow of photons. But the Big Freeze is not just about cold and darkness. It's also about the relentless stretching of space-time. As the universe expands, the distances between objects increase, not just in a linear way, but exponentially. This means that the space between galaxies will grow faster and faster, eventually reaching a point where it becomes impossible to travel from one galaxy to another, even at the speed of light. It is a sad thought that our galaxy may be isolated from all others in the far future. Consider the fate of our own solar system. Billions of years from now, the sun will exhaust its nuclear fuel and expand into a red giant, engulfing the inner planets, including Earth. Even if Earth somehow survives this fiery ordeal, it will eventually be ejected from the solar system as the sun loses mass and its gravitational pull weakens. Drifting through the void, a cold, lifeless rock, Earth will become a monument to a long-lost civilization. All evidence of humanity will be erased, leaving no trace that we ever existed. It is a sobering thought, but it is a stark reminder of the impermanence of all things. But the Big Freeze is not the only possible fate of the universe. There is another, far more dramatic scenario known as the Big Rip. In this scenario, dark energy is not constant, but rather becomes stronger over time, increasing its repulsive force. As dark energy intensifies, it begins to tear apart all structures in the universe, from galaxies to stars to atoms. Imagine a cosmic explosion, not just of individual objects, but of space-time itself. Galaxies are ripped apart, stars are torn asunder, and even atoms are stretched and broken down into their constituent particles. It would be a cataclysmic end, a final act of cosmic violence that would obliterate everything in its path. It might sound like a script for a summer blockbuster, but could the Big Rip actually happen? The answer depends on the nature of dark energy, something we still don't fully understand. If dark energy is a cosmological constant, as some theories suggest, the Big Rip is unlikely. But if dark energy is a dynamic field with a strength that increases over time, the Big Rip becomes a distinct possibility. It is a morbid thought to think that dark energy could rip us apart. Consider what it would be like to witness the Big Rip. As dark energy intensified, you would first notice that galaxies were moving away from each other at an accelerated rate. Then, you would see stars being pulled apart, their outer layers drifting away into the void. Eventually, even your own body would begin to feel the effects, as the atoms that make you up were stretched and torn asunder. It would be a truly terrifying experience, a final agonizing death. And then there is the third scenario, the Big Crunch. In this scenario, dark energy eventually weakens and gravity takes over, slowing down the expansion of the universe. Eventually, the expansion stops altogether, and the universe begins to contract. Galaxies begin to move closer together, temperatures rise, and the universe becomes increasingly dense and hot. Picture a cosmic rewind button being pressed, reversing the expansion of the universe and sending everything crashing back together. Stars collide, galaxies merge, and the universe becomes a chaotic, superheated plasma. Eventually, the universe collapses into a singularity, the same infinitely dense point from which it was born. It would be a symmetrical ending, a mirror image of the Big Bang, with the universe returning to its initial state. It is important to note that this scenario is now considered less likely, as observations suggest that dark energy is not weakening, but rather remaining constant or even increasing in strength. What evidence is there for the Big Crunch? There is not much at this time, but it is an idea that some scientists continue to study. String theory and its M-theory successors seem to have a Big Crunch baked into them. But even if the Big Crunch is unlikely, it's still a fascinating scenario to consider. It raises the possibility of a cyclical universe, where the Big Crunch is not the end, but rather the beginning of a new cycle of expansion and contraction. Perhaps our universe is just one in an infinite series of universes, each one born from the ashes of the previous one. But regardless of which scenario ultimately plays out, one thing is clear: the universe's beginning dictates its end. The initial conditions of the Big Bang, the amount of dark matter and dark energy, and the fundamental laws of physics will all determine the ultimate fate of the cosmos. These elements interact to write the story of existence itself. The Big Freeze, the Big Rip, or the Big Crunch. Only time, an unimaginable amount of it, will tell. And as we strive to unravel these cosmic mysteries, we cannot help but wonder if there are perhaps forces and phenomena we have yet to even conceive, factors that could dramatically alter the universe's trajectory. But regardless of which scenario ultimately plays out, one thing is clear: the universe's beginning dictates its end. The initial conditions of the Big Bang. The amount of dark matter and dark energy and the fundamental laws of physics will all determine the ultimate fate of the cosmos. These elements interact to write the story of existence itself. The Big Freeze, the Big Rip, or the Big Crunch. Only time, an unimaginable amount of it, will tell. And as we strive to unravel these cosmic mysteries, we cannot help but wonder if there are perhaps forces and phenomena we have yet to even conceive, factors that could dramatically alter the universe's trajectory. But what about us? Where do human beings fit into this grand cosmic narrative, a story that spans billions of years and light years, a story that began long before our solar system even existed? Are we simply insignificant specks of dust adrift in a vast and indifferent universe, or are we something more, something special, something unique? Consider this. Every single atom in your body, with the exception of some hydrogen, was forged in the heart of a dying star billions of years ago. That's right. You are literally made of stardust. Those population 3 stars that we mentioned earlier and their hypernova explosions are not only the first elements of the universe, they are also the ancestors of humankind. They scattered the elements necessary for planets and even for us across the cosmos. Every breath you take, every thought you have, every emotion you feel is ultimately rooted in the life cycle of these ancient stars. It is a humbling and awe-inspiring thought that we are all connected to the universe in such a profound and fundamental way. What did Carl Sagan mean when he said that the cosmos is within us? It truly makes you wonder about how and why we exist, but our connection to the cosmos goes even deeper than that. Not only are we made of stardust, but we are also products of cosmic evolution. The same forces that shape the galaxies and stars have also shaped us. Gravity, electromagnetism. The strong and weak nuclear forces all played a role in our development from the very first moments of the Big Bang to the present day. From this perspective, human beings are not just passive observers of the universe, but active participants in its ongoing evolution. We are the universe becoming aware of itself. It's a bit like what the philosopher Teilhard de Chardin once said, we are not human beings having a spiritual experience, we are spiritual beings having a human experience. We are driven by an insatiable curiosity, a desire to understand the universe and our place within it. From the earliest cave paintings to the latest scientific discoveries, we have always sought to unravel the mysteries of the cosmos. This drive to comprehend is not just a quirk of human nature, it's a fundamental aspect of our being. It's what makes us human. It is an endless cycle of questions and is what drives exploration. Exploration is what drives humanity, and it may be our salvation from extinction. It's this relentless pursuit of knowledge that has led us to develop the telescopes and detectors that have allowed us to probe the depths of space and time. It's this that has allowed us to formulate the theories that describe the origin, evolution, and ultimate fate of the cosmos. And it's this that has allowed us to contemplate the existence of multiverses. But it's also important to remember that our understanding of the universe is constantly evolving. What we know today may be overturned by new discoveries tomorrow. Science is a process of continuous refinement, and we must always be open to new ideas and new perspectives. It may be true that the Earth is an insignificant speck in a vast and indifferent universe, but we have something special. The ability to think and ask questions and to discover more about the cosmos we live in. The fact that we can learn about this incredible dance is incredible itself. It may just be a matter of time before we find the next big discovery. It could challenge everything. It's something that everyone is waiting for, and it may come sooner rather than later. The universe has waited 13.8 billion years for us to unlock its secrets, and that might be just the beginning. But it's also important to remember that our understanding of the universe is constantly evolving. What we know today may be overturned by new discoveries tomorrow. Science is a process of continuous refinement, and we must always be open to new ideas and new perspectives. It may be true that the Earth is an insignificant speck in a vast and indifferent universe, but we have something special, the ability to think and ask questions and to discover more about the cosmos we live in. The fact that we can learn about this incredible dance is incredible itself. It may just be a matter of time before we find the next big discovery. It could challenge everything. It's something that everyone is waiting for, and it may come sooner rather than later. The universe has waited 13.8 billion years for us to unlock its secrets, and that might be just the beginning. Think about it. From an unknowable state before time itself, we have journeyed to a universe of mind-boggling complexity. We've traced the arc from a singularity, a point of infinite density that defies our current understanding of physics, to the vast, expanding cosmos we observe today. We've witnessed the universe's explosive birth, the forging of the first particles, the dance of matter and antimatter, and the assembly of the building blocks of stars and galaxies. From those seeds, we explored the primordial elements and how they were forged in the furnace of the Big Bang. We then traveled forward in time to the release of light, dark matter, and the first stars and galaxies. It has truly been a journey of immense proportions. The evidence supporting the Big Bang theory is staggering, an intricate tapestry woven from countless threads of observation and experiment. The redshift of distant galaxies, a cosmic echo of the universe's expansion, the abundance of light elements, precisely matching the predictions of Big Bang nucleosynthesis, the cosmic microwave background, a snapshot of the universe in its infancy, all these pieces fit together to form a compelling and consistent picture of our cosmic origins. Yet, despite these triumphs, profound questions remain, mysteries that continue to beckon us towards the unknown. What existed before the Big Bang? What is the nature of dark matter and dark energy, those invisible entities that dominate the universe? Are there other universes out there, existing in a vast multiverse? And perhaps most fundamentally, why is there something rather than nothing? Why does the universe exist at all? What is outside the universe, or is the universe everything? It is truly hard to imagine. These are not just scientific questions. They are philosophical questions, existential questions, questions that touch upon the very meaning of our existence. They remind us that we are still infants, just beginning to grasp the immensity and complexity of the cosmos. It is a lot like we are standing on a beach looking out at the ocean. You can see as far as the horizon, but you know there is so much more beyond that. It is like the famous quote from Isaac Newton, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." Perhaps the answers to these questions lie just beyond our reach, tantalizingly close, waiting to be discovered by the next generation of scientists and explorers. Perhaps they will require a completely new way of thinking, a paradigm shift that will revolutionize our understanding of the universe. One thing is for certain. The quest to understand our cosmic origins will continue, driven by our insatiable curiosity and our unwavering desire to unravel the mysteries of existence. From the unimaginably small to the incomprehensibly large, from the fleeting moments after the Big Bang to the eons that stretch before us, the universe is a story of relentless evolution, a symphony of creation and destruction, a dance of energy and matter that has been unfolding for 13.8 billion years. And it is a story in which we are all participants. We are made of stardust, connected to the cosmos in ways we are only beginning to understand. We are the universe becoming aware of itself, driven by a deep-seated desire to comprehend the mysteries of existence. Even now, new discoveries are being made, new theories are being proposed, and new questions are being asked. It is an exciting time to be alive, a time of unprecedented scientific progress and discovery. So, let us embrace the enduring mystery and wonder of the universe. Let us continue to explore, to question, to imagine, and to push the boundaries of human knowledge. Let us never lose our sense of awe and curiosity about the cosmos and our place within it. For in the end, it is this sense of wonder that will drive us to unlock the deepest secrets of existence and to chart a course towards a future that is as vast and boundless as the universe itself. Are you ready to continue this journey of discovery?